If you are designing a system to store 100 petabytes of data, ensure 99.99999% durability, and manage 100 trillion distinct objects, standard architectural intuition will fail you. At this scale, the developer instinct to provision a larger disk or construct a traditional database architecture leads to a total system collapse. Let's define the baseline. Block storage relies on the raw, physical disk attached directly to a single server. It is extremely fast for bit-level operations, but it is strictly bound by the physical capacity and throughput of that specific machine. File storage evolved to make those blocks usable across a network. It layers a directory hierarchy, the folders and files we use every day, on top of that raw storage. But at the exabyte scale, this hierarchy shatters. A system managing trillions of files eventually exhausts its inodes, the data structures used to store file information. The computing overhead required to traverse impossibly deep folder trees brings actual data operations to a standstill. To survive a 100 petabyte load, we must abandon the concept of hierarchical folders and accept a radical trade-off in how data is organized. Object storage is that trade-off. We intentionally sacrifice low latency and in-place mutability to achieve infinite scalability and lower infrastructure costs. Instead of nested folders, we move to a completely flat structure. There is no directory tree, just a vast logical space. Because there are no directories, you cannot mount this storage to your operating system. Every interaction occurs via RESTful API calls over the network. Every piece of data is treated as a sealed, opaque box. You cannot edit a single byte within a file. To make a change, you must overwrite the entire object or create a new version. This architecture functions like a heavily guarded append-only warehouse. The engineering challenge shifts from managing local bits on a disk to the flawless routing of billions of individual data containers. To operate this warehouse, we use two primitives. First, the bucket, which acts as a globally unique logical boundary. And second, the object, which is the individual unit of data. Every object consists of two parts: the payload, containing the actual bytes, and the metadata, which holds the labels, permissions, and routing information. Scaling this to 1 trillion objects relies on a concept found in the original Unix file system, the inode. In Unix, the human-readable file name is separate from the file's data. The file name lives in an inode, which acts as a map pointing to the specific physical disk blocks where the data is stored. Object storage applies this principle at a global scale. It physically severs the architecture into two isolated brains, a metadata store to handle the mapping, and a data store to hold the payloads. This allows for specialized hardware. The metadata store uses high CPU servers for fast relational lookups, while the data store utilizes massive clusters of high-capacity, low-cost disks. Decoupling the map from the territory is the only way to scale a system to trillions of objects without creating a central bottleneck. In a global architecture, the client request hits a load balancer, which routes the traffic to an API service. This API service is a stateless conductor. It stores no data and exists only to orchestrate network calls. Because the API is stateless, it must verify permissions with the identity and access management module for every single read and write request. Finally, the API service communicates with our two decoupled storage engines at the bottom, the metadata store and the data store. This specific arrangement of stateless routers and isolated storage brains protects the system from cascading failures during traffic spikes. To see this data in motion, we can trace the exact sequence of a PUT request, a standard file upload. Step 1, the client sends the request. The API service holds the payload and immediately checks authorization with the IAM service. Step 2, once authorized, the API service routes the heavy payload directly to the data store first. Step 3, the data store persists the bytes to physical disk, generates a unique UUID, and sends that ID back to the API service. If the system updated the metadata map before the payload finished writing, a network failure would create a ghost file, a pointer in the database to data that doesn't actually exist. Only after the data store confirms the write does the API service tell the Metastore store to link your file name to that new UUID. This strict sequence, writing the cargo before updating the map, guarantees the integrity of the warehouse inventory, even during network failures. A GET request reverses this process and relies entirely on that metadata map. The data store remains blind to human file names. It has no idea what script.txt is. It only responds to fetches for specific UUIDs. Once the metadata store provides the correct UUID, the API service pulls the payload from the data store and streams the bytes back to the client. This orchestration works as long as the hardware stays intact. But at the exabyte scale, disks fail every single day. Separating metadata from data solves the routing problem, but surviving hardware failure requires replication and erasure coding. That is exactly what we will design in Part 2.